4 new TIMS modules enable a complete Signals and Systems course. The lab manual covers an introduction to signals, what are signals, what are systems, linear and nonlinear, what is convolution with a hands-on experiment, integration, correlation and matched filters. Also, it explores complex numbers as real signals, building a Fourier series analyzer. What is spectrum analysis? Poles and zeros in the continuous time domain. Introduction to sampling and aliasing and Nyquist. Getting started with analog to digital conversion, PCM signals, and then discrete time structures with FIR and IIR structures up to second order, all correlated to existing well-known textbooks such as Lathy, Oppenheim and several others. Skimming through the lab manual, you can see clear block diagrams, step-by-step instructions, preparation tutorial questions, graphs, and easy to follow. Let's take a look at Chapter 13, IIR structures. Viewing the block diagram and the patching diagram, the student simply patches together the modules according to the block diagram. A comprehensive on-screen control panel allows the user to change the coefficient values in the implementation, as well as create arbitrary waveforms required for each experiment via the tabs. Sweeping the input signal frequency through the IIR structure that has been constructed on the TIMS system, we can now view the input and output signals via the inbuilt picoscope that you have with your unit. And you'll notice the gain of the output is quite significant, and then it reduces. Looking at the Z-plane display, there are poles near the unit circle and a zero. Changing the patching of the modules, we can now use a broadband input signal rather than a single tone. Once again, we view the input and output, this time using the spectral capabilities of the scope. Here is the input and output in the time domain, back again in the frequency domain, a flat input and a peaky output. We can go in and adjust the coefficient values of the structure in real time, and by doing so we move the position of the poles or the zeros depending on what you wish to study. This reinforces the understanding of the relationship between the polynomial and the implementation. Changing A1, for example, you can see the frequency of the peak of the filter moving left and right. Varying coefficient A2 moves the poles closer or further away from the unit circle and allows the system to become unstable, which is very interesting. Moving from theory to real-world implementation in real time with real electrical signals helps students understand. A digital filter design tab on the on-screen control panel allows filter designs to be implemented as coefficient values and then studied with the real-world signals. You can see a Butterworth filter has been implemented, now switching to an elliptic filter, different response, different pole zero representation in the Z-plane, different coefficient values, and hence different implementation gains. And when we go look at the signal response of the real system, we can see that it has changed. It now has a slightly peaky output. Signals and systems is a complex and a very abstract topic. Help your students develop better understanding by using the hands-on TIMS equipment.